Day 134, Honors Electrostatics, Capacitors homework number 38. Once again, with practice, you'll start to identify very quickly where the parallel and series parts of this network is. This is not yet a circuit because we don't have a battery, but I will put a battery into this one as a kind of an extra bonus in a second here. But what we have here is, well, I've numbered some spots. Eventually, I'm going to connect a battery to point A. Down here, I'll put the battery, and I'm going to collect the other, say the negative side of the battery to point F. So what we're going to try to do now, though, without the battery first, is to simplify the circuit, reduce this to one capacitor. And once again, to try to figure out where the parallel and series parts of this network are, is if I'm at point A and I want to get to point F, I would go to point B, and I have two pathways now, so I know I have something parallel coming up if I have two pathways. That's always an indicator of parallel, not just parallel lines. So I can go this way to get to point C, or I can go from B down this way to get to point C. That means that this 0.25 and a 0.5 microfarad capacitors are indeed in parallel. And likewise here, you can see a similar thing. If I go from C to D, and from D I got to get to E and then to F, I have something similar going on. I have two pathways, the 0.1 microfarad at the top, or I can go down to the 0.2 microfarad capacitor to get from D to E. I have two pathways. Those are also in parallel. So here's one case where you can maybe do two steps in one. I'm going to simplify this. And the rule for parallel capacitors combination is pretty simple. You just add them up arithmetically. So we don't really need a calculator for that in this case. Bottom line, I'm going to add the 0.25 and a 0.5, and I will get 0.75 microfarads. And likewise, over here, I get 0.1 plus 0.2 gives me 0.3 microfarads. So I will draw that. So here's the new diagram. Now I've got this down to just two capacitors that are in series. Once again, I have the important points, point A and F, where I'll connect the battery eventually here. But it's just one pathway now. So if I'm going from A to F, I have one route to get there, assuming I can go through capacitors. You kind of imagine that you can. So those two are in series. Now combining capacitors in series takes a little bit more work. You have to use the equation 1 over C total. And here we only have 2, so it's a little bit easier, but you could have 3 or 4 in series. But it's the same fractional math. It's 1 over 0.75. I'm going to ignore the micro for just a few minutes and put it back in at the end. Plus 1 over 0.30 microfarads. If I go to my calculator and solve that for the total capacitance here, it comes out as 0.214 microfarads, but I rounded off to 2 sig figs, so I'm going to stick with that. I think the answer key has 3 sig figs. But that's the combined capacitance of all these capacitors. So that's how you would draw this as one single capacitor boiled down from the 4. So that one there is equivalent to the other 4 capacitors. It's not a real capacitor. It's a tool that we use to analyze circuits or networks or parts of circuits. All right, now is the bonus for this one. Here's the type of thing you might run into in a test. I'll say, okay, hook up a battery. So you'd have wires. This would represent a wire. And this would represent the positive part and negative part of a battery, a long and a short. So now we have what we call a circuit. We have a complete loop. I could label some points here. I don't really need to, like X and Y in these corners. And they might not even be corners. When wires are laying on a table, they're usually more round than this. But I now can traverse a circuit. If I'm an electron, essentially, though, the negative side of the battery is over here, the short side, and this is the positive side of the battery. What literally happens with batteries is it pushes electrons around from the negative to positive. And these wires are all full of electrons. They're not just one electron right here. As this one's moving to the right, there's also one over here moving to the right. There's one over here moving down. It's kind of like a chain reaction. We'll come back to that later. But bottom line here is you're going to have these problems on a test where I'll say, okay, simplify this, and now I'll figure out the charge and the energy stored on this replacement, or what they call the equivalent capacitance. This 0.12 microfarads is the equivalent capacitance of this circuit. It says it in the problem up here. The overall simplified capacitance of this circuit. But bottom line right now, what you will be doing is that once you get these diagrams drawn, is you'll be using C equals Q over V almost exclusively as you work yourself backwards from the simple diagram. For example, with this last diagram, my C is 0.21 microfarads. The micro is the important part of that. Equals Q. And let's say I have a 10-volt battery. Let me use a different color. a 10-volt battery, 10-volt potential difference. So that makes it pretty easy. 10 volts is the standard units. So that means, if I do the math here, Q, this charge stored in this capacitor, is 2.1 microcoulombs. If I cross multiply by the 10, so that would be the charge stored in this capacitor. And I could ask you for the energy stored in the capacitor, which then you just use the energy, which I'm not going to do, U equals 1/2 CV. Plug those numbers in, you can get the energy in joules stored in that capacitor or in the system, because that one capacitor represents the system. Now, but I might ask you, okay, how much actual charge is on each of the individual capacitors? Now you got to work your way backwards. And the rule is this. If I go to the intermediary steps, like this diagram right here, which is a tool, what you do is carry some of the information back from this diagram down here up to this diagram. What you carry back is this number right here. When you have capacitors, you carry back the charge, because it turns out that all capacitors in series have the same charge. They have the same charge as their replacement. That's one of the most difficult rules to remember. It's not a hard rule, it's just for some reason easy to forget. It's so easy it's hard. So this capacitor has a charge of 2.1 microcoulombs, and this one has a charge of 2.1 microcoulombs. That much positive charge on one plate would be the one on the left, and that much negative charge on the plate on the right. So now if you look at those two capacitors, this one and this one, you could calculate their potential difference, the voltage. Now it's not going to be 10 volts. They're sharing that. So when they're in series, they split that, but not necessarily equally. They would split it equally if they were equal capacitors. How do we figure out how much voltage each one of those has? I know it adds up to 10. It could be 8 plus 2, 6 plus 4, 7 plus 3. And a lot of times it's decimals, like in this case, but how do you figure it out? Well, the way you figure it out is by using C equals Q over V. I'm going to go way up here at the top. So C equals Q over V. So let's pick either one of those, the 0.75 microfarad capacitor, 0.75 micro equals the charge on there, 2.1 microcoulombs, divided by, technically it's delta V, which I leave off like most people do, the voltage, that should be a delta, don't have to put that on there, but the voltage there, delta V, will be the 2.1 micro divided by the 0.75 micro, so the micros will cancel out, and we get 2.8 volts. For that one. Now if you want to check for the other one, the 0.3 microfarad, so what I'm going to do, I'm going to write that down. So I have 2.8 volt potential difference for that capacitor. If I check with the 0.3, do the same thing, C equals Q over V for the 0.3, 0.30 microfarads equals charge stored 2.1 microcoulombs divided by its potential difference. So that potential difference for that guy comes out to be 7.0. Now I was hoping it was going to be 7.2. And why? Well, because 7.0 volts, that's a V for volts there. Well, because those two numbers here side by side, it represents these two capacitors over here in this middle diagram. I'll write that down, 7.0 volts. Those two black numbers should have added up to 10, because the total voltage in this circuit, or in this network part, this branch, needs to be 10. Because of rounding, I went back to 2 sig figs. Things are off a little bit, but that's okay. 7.0, 2.8, that gives you 9.8, which is close to 10 volts. Close enough. If you want to put 7.2 there for the second capacitor, you can. Now, you got to keep working backwards here. I'm a little out of space, but I'll show you what you would do. Is you bring information from each diagram up to the next diagram. So what information do you bring up from these diagrams down here? Well, what you bring up in parallel, these two are in parallel, this 0.25 and 0.50 in parallel. The rule is you bring up the voltage. Each of those capacitors is a potential difference of 2.8 volts. 2.8 volts. And the 0.1 microfarad capacitor, you bring up to 7 volts. If you want to bring up 7.2, you could have. 7.0 volts though. 7.0 volts, 7.0 volts. Now I'm not going to finish off this problem, but what I would say is it might ask you for the charge stored in each of those 4 capacitors. So what you do for those 4 capacitors is just simply plug into this equation again, C equals Q over V, for each of those 4 times, one individually for each one, you'll get a different answer because in the first case, the capacitance is 0.25 microfarads and its potential difference is 2.8. You'd plug those two numbers in for these two values and calculate the charge. It's going to come out in microcoulombs. And the way you would check this is the charge on these two is going to add up to the 2.1 microcoulombs. So the smaller one will have half the charge, so it's going to have about 0.7. That's real close. 0.7 microcoulombs of charge. This one will have about 1.4 microcoulombs of charge. And over here, same thing. This will have twice the charge stored as you plug into these equations over there. And they got to add up to 2.1 as well. Yeah, lo and behold, this will have about 1.4 microcoulombs of charge. This will have about 0.7 microcoulombs. The total charge stored will be this 2.1 microcoulombs. So the rule is this: when they're in series like this, they have the same charge. And you can figure out the energy stored as well. And in parallel, they have different charges because the bigger capacitor will store more charge, but they will have the same potential difference. Each one will. So that's a good example problem.